So the object of this talk is observer design, and we're gonna discuss about what kind of ISS-like properties we can obtain in this particular setting. And after reviewing the general case, I would like to share with you some recent research about a more original setting where we're going to assume that the system is not observable. So when you have potentially indistinguishable solutions and that you can still try to reconstruct, and in that setting, you end up with set-valued observers. And it turns out that there are some kind of ISS properties still in that context, but in terms of generalized distances, like Hausdorff distances, which I found quite interesting to show you. So before going there, let's try to start with the setting of observer design. So you consider a system which has some dynamics and some measurements, some outputs, and you would like to reconstruct the state. So the observation problem generally is you don't know the initial condition, and you want to find an estimate x hat of the state x of your system in real time, and based only on the past measurement that you had from sensors, for example, and such that asymptotically x hat goes to x. So it can be done in many ways, but in the observer literature, what we do is we try to write an algorithm here that's going to be fed with the measurement and reconstruct the state. And more particularly in the observer setting, we pick this observer as a dynamical system with state z hat here, and such that when you feed it with the measurement of your system and you compute some kind of nonlinear, potentially complicated map of z hat, you recover your estimate. So for those who are familiar with observer design in linear systems, in that case, z hat would just be x hat, sorry. So you would directly have x hat dot equals something, but it turns out that in nonlinear systems, it is usually not the case. And usually you have to rely on change of coordinates. That's what we're going to see together. And when you do that, then the state of your observer typically lives in a space that is not the space of the system. And then you have to come back to reconstruct your estimate. So it's quite well known that a necessary condition to build such an observer is to have detectability. So what's detectability is the fact that if you have two solutions that produce the same output, they must at least converge to each other. Because if they go to different places, then there is no way your observer will be able to say which is which because it has the same measurement. So that's typically a necessary condition. And then in terms of sufficient conditions, there are like an enormous amount of research on this topic. And every time you have some observer design based on different assumptions and usually on stronger observability conditions. But when you look at the literature, you find out that generally, as I was mentioning before, observer design relies on a change of coordinates. Because in general, you do not know directly how to write the observer in the x coordinate. You don't know how to write an x hat dot here. So what you do is you try to find a change of coordinates that puts the dynamics into a specific normal form that you find easier because for this form, you know how to build an observer. So that's why here you have a state that is called z, and you produce an observer, which is z hat. And then under some probably observability condition, you're going to be able to have an invertible transformation. And so you're going to invert this change of coordinate to come back to produce an estimate x hat. And so most of the literature is dedicated to what kind of normal forms do we know for which we know an observer, and then which conditions can we transform our system into those normal forms. And generally, they are based, as I was mentioning, on different kind of conditions. So I try to put a very rough review here just to give you an idea for those who may not be familiar with the setting. And in a survey that we did with my colleagues Vincent Andrieux and Daniela Stoffi, we categorized the observer designs into basically those 4 families. The first one is those which are based on what we call differential detectability. Those are basically the ones which, unlike what I was saying before, allow you to write the observer in the system coordinates. So they are built as a copy of the dynamics plus some correction terms. And the correction term just basically compare the measurement to the estimate. And so the peculiarity of those designs is that they are directly written in the x coordinates. But the issue is that they rely on some very stringent contraction conditions that concern quite a small class of systems, but still sometimes it's possible. Of course, for linear systems, it's possible. You also have a lot of LMI-based design where you assume some Lipschitz or sector condition on this nonlinearity, and you manage to find some gain here that works. But it's still quite restrictive. So the other class is, and this has occupied a lot of researchers in the 70s, it's the idea of saying, well, I know how to write an observer for linear systems, so let's try to linearize my system and find a change of coordinate that transform my system into some linear system. And in that case, if I am in a form where you have a linear dynamics with a linear output, then you have Kalman-like designs or Kalman designs, and there's some Gramian conditions, typically complete observability conditions. And the issue here is that first, the class of systems that you can actually linearize is quite small, but also you do not have a guarantee that even if your system initially is observable, it doesn't mean that the target system that you're going to obtain here will be observable, and so you will be able to find those gains or obtain convergence here. Then a great part of the literature is the observer designs based on differential observability and triangular forms. So the idea here is to look at the output and its successive derivatives, and to say that if the output and its successive derivatives are enough to reconstruct the state, then I can just try to reconstruct those derivatives. And in those coordinates, the dynamics are triangular, like this. And so you have a lot of designs, the Haydn designs, very famous, homogeneous, and all the sliding mode literature with the sliding mode differentiators. And the idea basically is just to add a correction term here, which can be either linear or homogeneous. And you have a gain L here that is pushed sufficiently large so that you compensate for the nonlinearity. And finally, a more recent design is the so-called KKL design, where the idea is to transform the state dynamics into this very simple filter of the output. So you're going to maybe wonder what is the difference between this and the one I talked about here. And it's the fact that here this is a stable filter of the output. So the output is not assumed to be or required to be linear in Z. So y could be any nonlinear function of Z, while when you were with Kalman designs, you had y that had to be linear in Z. And this allows you to reach a much greater class of systems and guarantee that you can obtain this form under just distinguishability conditions that we will come back later to. So in any case, this is sort of a big, very quick overview of the designs. And what you can see is that generally you you try to transform your dynamics into a specific form. And so you may ask, okay, but what happens with ISS in all this? Okay, so that's what I thought about for this seminar. And so let's say that you have some disturbances, maybe uncertainties in the dynamics or the output. and you build your observer and you wonder what's going to happen. So I thought about what could be called an ISS observer. And initially, so what people would generally write is this kind of property, which is that you have some KL and K functions such that for initial conditions that are in some sets, and this is quite important, I will come back to this, you have the estimation error, which is something that is asymptotically stable plus some kind of bound related to the disturbances. But the question is this the right ISS definition, and can we really call this ISS? So the first thing you may notice is that x hat minus x, contrary to linear systems, x hat minus x is not following independent dynamics. So it's not the state of a system. X hat minus x is just a part of the dynamics because you have, in fact, the state is x and the estimation error, or x and x hat. You cannot just look at the dynamics of the error. They are necessarily combined. So it's not really the state, it's more, let's say, an output. So you could say it's sort of an input output stability. But here you don't have, you only have here x hat minus x, you don't have x. So it is more in the sense of Sonntag and Wang, it's more like state-independent IOS. But of course, we're not going to say SI-IOS observer. So typically people will just refer to this kind of property saying this is ISS. But more importantly, I will try to show you in this presentation that in observer design, and especially when you change coordinates, in order to have this kind of property, you are forced to restrict the sets in which you take the initial conditions. Not in a local way, okay? This may be as large as needed, and the estimation is not necessarily small at the beginning, but still it should be in some manifold here. And so this constraint here makes this property not as nice as usual, because in particular, you cannot apply it between any times S and T, because those sets are not invariant. I will show you that. And so since those sets are not invariant, you cannot apply this from between any time T and S. And in particular, you cannot relate this gamma to an asymptotic gain property. So some researchers, oops, sorry, there is an issue here, have proposed, and it's a paper by Alan Rawlings and Thiel, to talk about instead robust stability and to add a penalization here of your past disturbances. And in particular, you want to say basically that the disturbances you may have had in the past may not affect, if they disappear, in particular, if this goes to 0, you want to say that the estimation error is going to go to 0. And for this, you kind of need some penalizing term, which in this paper, they just take as another KL function. And in that case, you recover the nice asymptotic gain property that we like in ISS properties. And again, this is all because you're forced to restrict the initial conditions, and I'm going to explain you why just in the next slide. So let's come back to the change of coordinates I was telling you about. And generally, what happens is that you design your observer here in the Z coordinates. And so in all the designs I mentioned, the high gain, the KKR, etc., you have typically ISS conditions in those coordinates, okay? So generally, you don't even have any restriction on Z hat. You could have, like in the Kalman design, but even if you don't have any restriction, okay, you have this kind of property. So this is in the Z coordinates, and you may want to ask, under which condition can you say that you recover this nice property in the initial coordinates? So let's try to see together. The first thing you want to do, of course, is to go back. And you kind of imagine that the way you're going to go back needs to be somehow uniform. So you're going to assume generally some uniform injectivity both in space and in time, which is going to allow you to at least come back to x hat minus x as bounded by a z hat minus z. So this is going to give you this kind of thing. So how far are we from ISS here? Well, we have three issues. The first issue is that this is still z hat minus z and not x hat minus x. The second issue is, and I didn't insist too much on this, here you have a noise or a disturbance that is not the same as here because you change the coordinates, okay? So this is something that depends potentially on v if you have y here, but also on the Jacobian of t, and you have something here which is not w. And also, in the case where t is time varying, there are a lot of designs where you obtain injectivity only after a certain time. So in that case, of course, there's nothing you can do. You will only obtain properties about x hat after t bar, okay? But we can still work a bit on that. So in here, what you can actually say is that at least the z0 is the image by t of the initial condition of x. And so this is what I was telling you about restricting the initial condition on z hat, is that if you want to come back to something that is in x hat minus x, you need to constrain z hat here. And in particular, you need to constrain z hat to be the image by t of something. So what we do in general is that we pick z hat 0 as the image by t of something in the set in which solutions are known to be. And this is quite natural because if you know that your solutions are in a set and you know that you have done a change of coordinates t, then of course you're going to take an initial condition in z that is t of something, okay? But if you don't do that, you may have z hat minus c that is not 0 and yet x hat minus x that is 0. And the reason is that I didn't insist too much on that, but a peculiarity of nonlinear systems is that not only do you have a change of coordinates, but the space here that you obtain may be of larger dimension than the state in the initial coordinate. This means that the image, this space here, is just at best a manifold. So it's something of just a manifold. And if you initialize z hat outside, then you cannot upper bound z hat minus z by something in x hat minus x. So the way you do it is that you force z hat to be the image of something, and you obtain, and you of course put some kind of condition on the continuity of t at time 0, which is usually uniform continuity. And then the last issue was w prime, so you have to have something that tells you that you can upper bound this disturbance here by something that depends on w and v. And this is generally the case because in particular when the solutions you're looking at are bounded, because this w prime is typically something that depends on x and v. So as long as x is bounded, you can upper bound it like this. So you need those three things to be able to come back, and you need to restrict z hat of 0, and that's why before I had this restriction on the initial condition. The only thing you cannot remove is this fact here. So of course, if your transformation is injective only after some time, you will have nice properties only after some time, okay? But in the autonomous setting, when t is independent of time, you don't have this problem anymore because you just injective and that's it, okay? Oops, sorry, I don't want to. Sorry, I skipped that. Yep. Right. So this was to tell you some thoughts about how to guarantee ISS properties in observer design when you are change of coordinates. And now I would like to tell you more about, as I was saying before, a more original context where you try to build an observer for a system that is actually not observable or not distinguishable. So why do we do this? Like, where can we find indistinguishability in applications? Well, the first reason we tried to handle this topic was that, unlike for linear systems, where indistinguishability is necessarily an infinite dimensional space, no, sorry, finite dimensional, but with an infinite amount of elements, in nonlinear systems, it may occur that there are only a finite number of indistinguishable states, solutions. Okay, so this happens typically in electrical machines. For example, if you take a PMSM, for those who know a bit about this kind of systems, if you measure the voltage, you measure the current, and if you say that you don't know the resistance, we showed that actually there may be, and there is actually, two indistinguishable solutions that corresponds to two possible resistance, okay? But there are only two of them. And so as soon as you have only a finite number of possibilities, it is quite tempting to try to build an observer whose role is still to estimate those finite possibilities, okay? And this has been looked into by some authors like Rémi Moreno and Gildas Besançon. In the case of, they introduced some kind of non-observable cascade form. They did some sliding mode design. But what I'm going to show you in this presentation is that also the KKL framework is specifically adapted to this kind of situations without making any assumptions about the structure the dynamics may have, and allows you to reconstruct the finite number of possibilities. You may have other applications, of course, where maybe you have an external information that is going to help you dissociate afterwards among the different possibilities, or maybe you just want for safety to know that the state is in a specific set. And so even if it's still several possibilities, as long as they're in some set, then maybe you're happy, or this kind of setting. And the other motivation I want to tell you about is hybrid systems with unknown jump times. So this is quite different. So hybrid systems are systems where you may have both continuous time and continuous time dynamics and also discrete behaviors in some specific set. And for example, the most intuitive thing is if you take a bouncing ball, the ball, as long as it is in the air, it evolves continuously, but then when it hits the ground, you have an impact that is a super fast event, and that you can model by just the discontinuity of the velocity, because the velocity is going down, and when it reaches the ground, it's immediately going up. Okay, so this kind of setting allows you to model some systems with impacts. It allows you to model also switch systems where you have discrete events, these kind of things. And an important part of this literature is to, of course, design observers, but the problem is when you cannot detect that there is an event that happens, that there is a jump or discontinuity. So this typically appears, of course, when the measurement does not change at the jump. So you see here, the value of the output after the jump is the same as the value of the output before the jump. So in that case, you cannot easily detect it. So of course, if you measure, for example, the height of the bouncing ball, then you're going to tell me that as soon as you see that the ball is on the ground, you can trigger your jump. But you can imagine that those kind of detections are not very precise. And in particular, in biped walking, where you have impacts that are not very clear with a foot and impact sensors that are not very precise. So you would like to avoid having to detect opportunities. And another context is for switch systems, when you have uncertainties in the parameters that allow you to say that you're going to switch among different dynamics. And in particular, we encountered this in drilling applications with the so-called stick slip phenomenon. So for those who know about it, it's mechanical systems when you have dry friction. and you want to control them, sometimes you may enter into some oscillatory behavior between moments where the object doesn't move because the drive force is too strong, and then the moment where the force gets higher, it's going to move, right? And it's going to oscillate between stick and slip, and the coefficients and the parameters that allow you to say when you're going to switch between those depend on, okay, the parameters that you typically don't know, okay? So in all those contexts, you would like to do observation, estimation, but not detect any discontinuity or any event. And the problem is that, as you can see here, the fact that you have no jump detection, so that the jump is not seen from the measurement, is that you're going to have points that are indistinguishable, meaning that the state, for example, if you take the bouncing ball, the state before the jump with the velocity going down and the state after the jump with the velocity going up are indistinguishable. They trigger the same output history, both in backward time and in future time. And so this is also an application I will tell you about, and that leads to interesting ISS conditions. So to go there, I need to tell you a bit about KKL. So KKL observer design, the idea, as I was saying before, is to try to find a change of coordinates that transfers the system into this kind of dynamics, which is just with A of it. So this is just a filter of the output. And so you filter your output, and then you try to see whether the Z hat, which is converging to T of X, contains enough information for you to recover X hat. So basically, you ask yourself, is it invertible? So this design comes from Leuenberger initially, because unlike what people are used to when saying Leuenberger observer, when this guy started to write about observer, his idea was really exactly that. So his idea was, I'm trying to find a linear change of coordinates, for us it's going to be nonlinear, that transforms my dynamics into this stable form, and then I find out conditions, and it's going to be observability, that allows you to have invertibility of this. And this is exactly how we wrote it down, but it's just that for linear system, it turns out that this is completely equivalent to the usual formulation that people have in mind when speaking about Leuenberger observers, which is just X hat dot equals copy of the dynamics plus a constant correction term. But unlike for linear systems, for nonlinear system, writing X hat dot equals, as I was mentioning before, is really restrictive, while trying to do something like that and allowing the dimension here to be larger than the dimension of X is going to help you and to give you some results about observer design, some existence results that are super general and that just ask some basic distinguishability conditions. And so typically initially they tried to do that locally, and the breakthrough happened with this paper by Vincent Andrieux and Laurent Praly, where they actually showed this, which is that under a simple observability condition, you could find this map T, and it was actually injective. So in this presentation, we're going to forget about observability, and we're just going to say that generally what happens, and I'm going to give you the result just after, T always exists typically, just under some regularity assumptions. Finding T that maps you into this is not a problem. What is a problem is to go back, okay? So T of X can always be estimated, and you want to know what can you know about X that is given by T of X. Okay, so this is the main result. Sorry about the technicality here. I just wanted to tell you what it looks like. And so what we showed here in this Knuckles paper is that you take like a general system, and under some basic regularity conditions, you're going to be able to say that for almost any pair of a sufficient dimension, which is linked to the dimension of X, then you have your T, so T exists. And more importantly, this T characterizes the states that are indistinguishable, meaning that T is not injective. So T of XA equals T of XB does not give you XA equals XB, but it gives you XA and XB that are backward indistinguishable, meaning that they generate the same output in backward time. And you can think that if you can reconstruct X modulo all its indistinguishable states, then you're happy because there isn't anything you could do more, in the sense that those states, anyway, they are indistinguishable. So there is nothing you can do to distinguish them. So if you have something that allows you to recover them, then you're very happy. And so what you're going to do is, as soon as you know this, you're going to try to invert your map T. So of course, T is not injective anymore, so I cannot write T minus 1, okay? But I just look at the pre-image, so all the points that could have produced Z by T, okay? And this theorem tells me that this is exactly the states that are indistinguishable from X. And this, just to introduce this notation to simplify in the future, I call this calligraphic I like indistinguishable sets, which are all the states in X that are indistinguishable from this small x. And so from now on, what is tempting is to run this filter, because this, you know, converges to T of X. Remember that here, because the T of X follows these dynamics, and those dynamics are contracting, even if you initialize Z hat to any initial condition, you know that Z hat goes to Z, which is T of X. So you know that by running this, you're going to go to T of X. And so now you just want to invert T and find all the backward images that you can find. The first thing you have to be careful about is that Z hat, remember that T of X is just a manifold, okay? So Z hat is not necessarily in the image set. So you have to find some kind of extension of this inversion. That is okay. Maybe you can, for example, there are many ways you can do that. You can do projections. There are a lot of ways you could do that. Sorry, you could do that. A possible way is just to find the X, which is a set, right? Here, I'm not saying that this is a point. I'm saying it's a set. It's a set of points that minimizes the distance between T of X and Z. And so here is what we obtain. We know that Z hat goes to T of X. And we know that this T-inf gives you the indistinguishable states. So the natural question is, can we say in some sense that the inversion of T applied to your estimate is going to converge to the set of indistinguishable states? And you obtain a problem of set convergence, right? Because now you have sets. So just a quick example to give you an idea. If you take this very simple two-dimensional system with this output, you have a symmetry. You have a symmetry, and the symmetry is not broken by the output. And so all the points X and minus X are indistinguishable. They trigger the same output at all times. So you can still try to run the KKL observer. So what do? You take your output, you filter it, you compute the map T that I was telling you about before, and we can come back to this point if you're interested. And then you try to solve. So this we did in a very stupid way with some basic gradient descent algorithms. And what we obtained is that indeed at all times, it was converging to either X or minus X, right? So here you see that it was kind of switching. So here it was minus X, and then here was the other one, etc. And here, for example, where we try to initialize better the optimization and we enforced continuity, we had just minus X all the time. So indeed, this confirms that in T of X is contained the information of X and minus X, right? But you still want to know, okay, what convergence can we state and what kind of ISS property can we have, right? So the first thing to say is that you have to be careful with the convergence of sets, okay? So here I give you some example very quickly, which you have x here and z here, okay? And imagine that your x is going to 1. So x is going to 1 here, and so t of x is going to 0, but from below, okay? So as x goes to 1, z goes to 0 from below. So when you invert t, you have those 3 green points, right? The pre-image, those 3 points. Whereas if your z hat, for example, is going to 0, but from above, right? You will obtain those green points here. So you see that you have the intuition that in terms of set convergence, you cannot really say that these green points converge to those green points in any way. They do not tend to be included in one another. The only thing you can say is that this set tends to be included in the red set, which is the final one. Okay, so this can be quantified in terms of a metric, which is called the Hausdorff distance, which is used to compare sets. Okay, so the Hausdorff distance is something that will be 0 only if 2 sets are equal. And so here we see that on this example, we do not have convergence of those sets in terms of this Hausdorff distance. So what we try to do with Mohammed Magnenem is to provide conditions under which you have this convergence. And those conditions we find out was the fact that you need to have a constant number of indistinguishable states. Remember in the example before, the number of indistinguishable states was always 2 unless x was 0 because you have minus x and x. Okay, so this needs to be constant, and the rank of t needs to be full rank, which allows you to have some nice behaviors. And under this condition, you can show that you can build an inversion of t that is Lipschitz, and that guarantees Hausdorff convergence. And so then for this seminar, I asked, well, what can we say about ISS conditions in that context? And in particular, you imagine that you have disturbance now. So you have your disturbance here. When you change your coordinates, you end up with something here, okay? And then, of course, in the z hat, everything is easy because z hat is just a linear system. So, of course, you can say that z hat minus z is going to be ISS with respect to W prime, okay? So this is what I have here. What you can show is that when you compare the estimated set to the indistinguishability set, you're at least having some kind of nice property here, which tells you that this is going to be some kind of ISS-like thing here. But here you have z hat minus z, so doing exactly the same kind of reasoning that we did before for the standard single value case, you can show that you can come back to a difference between t of x hat minus t of x, and this is because you force your z hat here to be initialized in the image set of x, and this you can relate to exactly that. I'm not going to spend too much time on this, and so at the end, this is the final thing, you obtain ISS, so exactly the same kind of ISS I had initially, but in terms of the Hausdorff distance between the estimated set and the set of indistinguishable states corresponding to x, okay? So it's just the metric that changes. You have sets, you have Hausdorff distance instead of just x hat minus x, but you can still recover exactly like usual some kind of ISS-like behavior. And so the application I was mentioning before is for hybrid systems with unknown jump times. So remember I was telling you that in this context, you had an issue because the discrete events were happening at times that you don't know because the measurement does not change at the jumps. You cannot see anything from the measurements. So you don't know when to trigger the discontinuities in your observer. You don't know when to trigger the impacts. And more importantly, x hat minus x, which is the standard Euclidean distance, no longer makes sense now, because around discontinuities, when you look at x hat minus x, you can imagine that you will always have, even asymptotically, always have x hat maybe that is slightly ahead or slightly behind x. So you will always have some irreducible distance between x and x hat around the jump times, unless they are perfectly synchronized, and this you cannot do because you don't know when to trigger the jumps. So you know, before anything, you know that x hat minus x will not go to 0, and you have to look at other distances. And as I was mentioning before, you have an indistinguishability problem, because precisely always the same, the value before and after the jump, before and after the discontinuities, they are completely indistinguishable. And so what we do, the idea is to say, well, it still makes sense to apply KKI here, because the output here is continuous in time. It does not jump at jumps. So Y is a continuous time signal, let's say. So you can still implement this filter, it makes sense. And the question is always the same. You run this without any jump detection. It's just a continuous time system. And do you have enough information in Z hat to reconstruct X? Always the same. And by doing exactly like with the same tools, we submitted actually for the next CDC a paper about the existence of this change of coordinate that we call a gluing change of coordinate, because what is interesting here is that you see the Z is going to be an image of X by some change of coordinate, but Z does not jump. Z is continuous. So you have this gluing property, which says that the value of T before and after the jumps are the same. In the new coordinates, you are continuous time. Okay, this is what we call gluing. And more importantly, if you are distinguishable outside of the jumps, you can show that T is injective everywhere except on the jump surface. So it means that as long as you're outside, you're injective, so you can produce uniquely your X hat, and it's just around the jump times that you don't know if you're before or after the jump, basically. So this idea is not new. It was introduced by those authors in 2019, actually before in the conference version. But here the difference is that you have a systematic way of building this change of coordinate and a systematic way of building the observer, okay? Because in this paper, what they did is try and give this, which I find very cunning idea of gluing, and they proved that it always existed, this change of coordinates, but without any clue about which kind of dynamics, continuous time dynamics to look for. And this approach tells you that you can just fix the target dynamics to be just this filter, and then the T will exist, and you will guarantee under, of course, as exactly as before, a condition on the dimension of A and B that T is injective outside of the jumps. And so, in fact, what you have here is a type of injectivity which is not, again, T of XA equal TXB implies XA equals XB, which is typical injectivity. Here, it is equivalent to XA and XB being this set, which is either XA equals XB, or XA is a bit behind, so XB is the same as XA, but after the jump, or here the contrary, or they are both after the jump. And so if you look at this set, then you can prove convergence of your observer. But instead of proving that X goes to X hat, you're going to prove that the distance to this set goes to 0. Okay? And what is, again, very nice is that because in the Z coordinates, sorry, I come back to show you. I know I didn't write it down, sorry. In the z coordinates, this guy here is perfectly ISS with respect to some noise, for example, in y. The z hat minus s minus z will be ISS. And so you can recover, again, exactly as usual, this ISS property for the estimate, but in another distance, which is not x minus x hat, but this distance to this, we may call this a peaking free set, because the phenomenon that you cannot have a convergence of x minus x hat to 0 is called peaking in this literature, meaning that you always have an irreducible error around the jump times. So this set here removes this problem and allows you to quantify something that actually goes to 0, plus some errors that will be just produced by the measurement noise. And so, for example, if I show you in this bouncing ball thing, which is a very simple example, what happens? So sorry for this. So when the ball is in the air, it just follows a two-order, very simple system. I put here some friction. As long as x1, which is the position, is above the ground, and x2 is the velocity. And when x1 hits the ground and the velocity is going down, you're going to produce a jump, which is to change the sign of the velocity with some restitution coefficient that may be smaller than 1. And just to prevent here having some problems, I added some energy here at the jump. And so here is what it looks like. So in there, you have the z coordinates. So you see everything is perfectly continuous here. There is no discontinuity. And z1 hat goes to z1. It's just a simple linear thing. And then when you come back to x and to x hat, you see here that even if x2 jumps, so you see here the discontinuities between negative, positive, you have convergence with maybe some errors around the jump times, which are just due to the fact that probably here the red curve is just a bit late, for example, and jumps just after that. And in terms of the distance to the set A, though, this converges to 0. Okay? And so now I made the exercise to adding noise. And if you add noise here, so here it's easy, it's a linear system, but you see here what's going to happen is that you're still going to have some kind of robustness and ISS, but in terms of the distance to the set A that I was mentioning. And in particular, you can see here, especially here, that some small errors due to noise may lead you to make a mistake between before and after the jump. So you have here maybe some oscillation a bit around the jump times. And so, of course, you see that if you were looking at x hat minus x here, you wouldn't be able to say that it converges to 0 because of those discontinuities and the slight errors that happens around the jumps. But in this new distance, you have everything that is accepted. So I reach now my conclusion. So what did I want to say in this presentation? I first try to tell you that you have to be careful with change of coordinates and ISS conditions. That in observer design, usually if you want to recover ISS property and even just stability properties in the initial coordinates, you have to have some uniform injectivity and continuity properties. And more importantly, you may have to restrict your space of initial conditions. And sometimes you get injectivity only after a certain time. And then I showed you 2 cases of observer design, which is set valued in some sense. In the case where you're not observable, and we saw that the KKL approach was very adapted to that, because it could provide you Hausdorff convergence and even Hausdorff ISS to the indistinguishable sets, which is very helpful in hybrid systems with unknown jump times with ISS-like properties, but instead of being in the Euclidean context, you are in terms of distance to a appropriately chosen set. So this is roughly all I wanted to tell you about. I really thank you for listening, and I hope we can have a discussion now about all this. I'm very happy to have any of your questions.